Okay, welcome to lecture on Chapter 2 of Network Fundamentals. This chapter goes into a detailed explanation of reference models for networking communication and a basic explanation of what networks are. What we're really going to do in this particular chapter is we're going to look at what a network is, what the models are, how a message gets encoded from a sending source to a destination. This is an example here, and here's one of the ideas of we're trying to describe a sunset between one caller and another caller. Well, the message source has to encode that information in some way, send it across a particular medium or media, and then on the receiving end they have to decode it. In other words, as this relates to networking, we're going to see that we encapsulate information on the sending side and we de-encapsulate it on the receiving side. And this process is how we go about allowing two devices or hosts to communicate over a network. Here's an example of two concepts that we need to find in order to understand networking. One is segmentation. Now, segmentation is taking a message or a large message, breaking it into smaller parts. This is going to be important as we learn about things such as packet switching and circuit switching, especially packet switching networks, or networks where we take a large piece of information, break it into smaller pieces, send it out onto the network, and then have it received on the opposite end and have it reassembled. So segmentation is breaking it down into multiple smaller pieces. Multiplexing is how we share the bandwidth. So we only have one link. We don't want collisions. We want to make sure that we can efficiently use the bandwidth of a link. So what we do is we figure out a way to interleave the pieces. You will learn down the road that this is done mainly by timing and synchronization bits, so that we can time the way that pieces of information go on to a particular media or medium. So that's just two concepts I need to throw in here so you can kind of understand how the pieces are labeled. You know, that really is an important thing for your students to understand. We take our messages when we ask for a web page. We don't just send one big request for give me www.nfl.com. No, we break that request down into a bunch of little pieces or packets, and those packets are sent out, alright, and then once they reach the destination does what it needs to do, looks at what information has been requested, and then sends back in a series of packets the requested information. Well, in order for this all to work correctly, we're going to have to have a way to reassemble these particular pieces, these segmented pieces, as they get sent and then when they're sent back. Well, that's eventually you'll learn about sequence numbers and how those sequences are kept up with. But at this point for you, it's just important to understand we take these large messages, break them into smaller pieces, label them, send them to the destination. Destination puts them all together, looks at what it is, what kind of request it is, and then returns back a series of packets that also then answer that request. Now, a network has devices, we've talked about this already, a media, and then services, which I will also say are protocols. So I would really say the one thing missing in this definition is there are devices, media or medium, protocols, which are not shown in this particular item here, and then the services that are provided by the protocols that are used. And then end devices are where data originates and the reason for those services to exist. And this kind of shows you the end devices versus the intermediary devices. You know, an end device is going to be a host, a printer, a PC, an iPad, an Android tablet. The intermediate devices are the routers that are shown in this particular internetwork that take the information and ensure that it gets sent to the correct network and then is also returned. So here's our intermediary devices. They don't change the data, they don't generate data, they just move the data from one network to another network. Whereas end devices generate data or generate data request and also then generate possibly data as a response to a request. Here's our different medias. We have copper, we'll talk more about these later. We have fiber optics, we have wireless. All of these will be covered on our chapter on the layer 1 of the OSI model, the physical layer. Now, we have multiple types of networks. This is something your students need to understand and you need to understand. We have local area networks. These are networks that are within a limited geographical area. That's how you remember it. Local equals limited. Now, you could still say, even though we have multiple buildings on our campus here at Stanley Community College, most people would call this just a LAN. There was a term in use called a campus area network, a CAN. Some people still talk about those, but for the most part, we'd just say that Stanley Community College is 7, 8 buildings. They're a LAN. They're just one group of networks under the control of a single entity. Now, another type of network is a WAN. That's a wide area network. That's a network that has no geographical boundaries. The most famous of that, of course, is the Internet. You know, the Internet spreads around the world. There are no geographical boundaries on it at all. There are all different types of networks. Okay, here's my cell phone. You heard it go off just a little bit earlier. If I had a Bluetooth and my cell phone, that would be what's called a personal area network. That's a network where it's within literally the space that is occupied by a human and the devices on it. If any of you have an iPod, one of the little iPod things that go, or that's a little pod that goes in your shoe or on your shoe, and it connects to your iPod, and then that sends data to you, that would be a personal area network. You'll see a much bigger growth on those types of networks as we continue to use those devices. I have a heart rate monitor. That would be a personal area network. It's literally a 2.4 gigahertz device. So LANs, limited geographic area, WANs, wide area networks, CANs, campus area networks, PANs, personal area networks, and another one's pretty common, a MAN, metropolitan area network. That would be if I had multiple sites in a single city and those were connected together. Now, again, here's two LANs connected together. That would be considered a WAN because it's not in a limited geographical area. And the biggest of that is the Internet, just like we talked about. Okay. Here's some common network representations that you'll need to know. This is the common logical symbol used for a router, switch, hub. Hubs are of the devil. Okay, that's what I always teach my classes. There are very few places in a modern network you should have a hub. One of the only ones is if you're trying to capture traffic without using a span port. A hub can be useful in that respect, but otherwise hubs, since they're shared access and shared resource, you need to be very careful with them in any network. I wouldn't suggest them at all. Servers, desktop computers, laptops, wireless media, LAN media, WAN media is a lightning bolt, which is usually synchronous, asynchronous, wireless routers, wireless access points, IP phones, and firewalls. You'll see these constantly in the Cisco curriculum, and so this is something you just kind of need to commit to memory. Now, one thing here, Packet Tracer. What is Packet Tracer? Packet Tracer is a program that's available for you to use for your for you and for your students, and it's available when you log into cisco.netacad.net, the Network Academy connection. On the left-hand side, you'll see a link that says Packet Tracer. If you click on it, you can download Packet Tracer 533 and install it on your local machines. This will then allow you to click directly onto the packet tracers in the curriculum, and it will pop up a packet tracer window and will start Packet Tracer so that you can actually create. Okay, this is just exploring the Packet Tracer interface, locating key components. This tells you what Packet Tracer is. It allows you to create simulated networks. You can literally pull out a 2811 and you can go into that 2811, go into command line and see that it's booting. Okay. You'll notice that I can't do anything with config. There are no WAN interface cards in this router when you just pull it out in this way. And it actually, this walks you through a little lab so you can actually do that. But notice if I go in here and try to find a WIC 2T and I'm going to try to put it into the router, it says nope, can't do that because it's powered on. So you literally have to power off the router, put the WIC 2T card in, put in some WIC covers, put an NM cover in, network module cover, and boot the router back up. You can see the router booting again. Now you're going to have a 2811 with one WIC card in it. So this is a tool that your students will be using throughout the semester to allow you to give them practice in a simulated environment. And like I said, you can see it's a 2811 simulated router. And it is a simulation. This is not like our NetLabs. NetLabs is not a simulation. This, however, is good for practice for your students, just for quick hands-on stuff. You can let your students use this as a practice tool. But these packet tracers you can do on your own. I'm not really requiring them as part of this course because I prefer for you to do the real hands-on labs in our NetLabs. But this is something you need to teach the students so they can start using it for themselves. This lab is just NeoTrace. It may or may not work on your network because it requires ICMP echo requests and echo replies. We block those on Stanley's network, so this lab may not work in your particular environment. Here are some of the rules, protocol suites. We talked about this. We talked about this in Chapter 1. Protocol suites are a set of protocols that work together to enable the communication process between a sending host and a receiving host. Now, these rules, okay, have a common language. They go by standards. It would be just like if I'm speaking French in this particular video and you don't understand French, you wouldn't understand me. I barely speak French, by the way, so I won't try that on this video. But it is a set of rules that allows you to send information from one host to another and vice versa. The biggest thing is formats. How do we structure our requests? How do we encapsulate our information in that, the process of breaking it down into segmentation? How big are the segments? What is required in a segment? What's in the headers? All of that's part of the protocol specification. We'll talk about these as we move through, talking about the different layers of the OSI model. We're going to show you an Ethernet header. We're going to show you a TCP header, TCP/IP, actually just TCP headers and UDP headers and IP headers. All of these things that are formats, and those are determined by the protocol suite and the protocol rules. For TCP/IP, those rules are governed by requests for comments, or RFCs, because TCP/IP is an open standard. Error messages. What do you do when a piece of that particular segmented request doesn't make it to the destination? What do you do? Do you retransmit the whole thing? Do you retransmit just the missing part? That's the kind of thing that the rules that are associated with the protocol help establish. And then how do you terminate a session? Depending on whether you're UDP, which is connectionless, which waits a certain amount of time, or TCP, which is connection oriented, which says, no, it's an end. We end now. So here's the fin bit, our conversation is over. Those rules will tell how you terminate a session between two hosts. So here we go again, just talking about the different standards that are accepted. Okay. Here are a couple of the different protocols that are part of these are built into the TCP/IP protocol stack, part are not. For instance, in the TCP/IP protocol stack, we have the application layer protocol called HTTP. It handles web interactions and web traffic. TCP is a transport layer protocol that is connection-oriented, guaranteed delivery. IP is the network layer, or the internet layer protocol that actually, internet layer protocol, if you're using TCP/IP model, that allows for delivery between different networks. So path determination. It's not connection-oriented though; it's connectionless. And then Ethernet. Ethernet is not really part of the protocol standard. Ethernet is just a layer 2 standard that TCP/IP can work with. And it's actually one of the strokes of genius we'll talk about with the TCP/IP protocol suite. When they built it, they did not specify any lower layer 1, layer 2 specifications for TCP/IP to run on. This way, it can run on 10 megabit per second Ethernet. It can run on token ring. It can run on gigabit Ethernet. It can run on 10 gig Ethernet. It can run on wireless. It can run on carrier pigeon. It doesn't matter. As long as you follow the standards for layer 2 that are specified, layers 3 through 7 can actually work for TCP/IP. Now, technology independent protocols, that's what TCP/IP is. It doesn't matter. It runs on iPhones. It runs on Android devices. It runs on PCs, Macs. As long as you follow the standards, it'll run on anything. That's why it's the ubiquitous protocol stack now. Here's where we're going to talk about models. and this is how I always start out my discussion of models. Growing up, I used to build plastic models. I built F-16 fighter planes, my favorite. The F-16 fighter plane, even the best model you can buy, a Hasegawa model from Japan, the best models may have 250 pieces in it. I actually ask my students, how many pieces do you think a $100 F-16 model has? They say 80, 100. I say, well, you can get up to 200. I say, now that is a plastic model of an F-16 fighter plane. How many pieces do you think there are in a true F-16? And they go, millions. Exactly. So in other words, no matter how good the model is, no matter how well made or well thought out it is, it typically does not fully explain or represent the process that the model is trying to represent. In the case of the OSI model, which is a layered model for communication between a sending host and a receiving host, there's some ambiguity, and there's also some lack of representation of different pieces of the communication process. That's because it is a model. It is not the actual process. We do have an OSI protocol stack. Nobody uses it, but we have it. So you're going to look at TCP/IP and go, but it doesn't follow the model. Right, it doesn't, because it was created before the OSI model, and the OSI model is just a model of communication between two devices. But why would we even want to use a model? Well, there's a couple reasons. One is it does allow for the interaction between multi-vendor networks. If I say something is a layer 3 device, that means it's a network layer device. We all know, well, we will know once you learn the OSI model if you don't already know it. We will know that a layer 3 device, this is some type of router or routing device that handles path determination. Why? Because I know that layer 3 in the OSI model is the network layer, and that is designed to do path determination. So one reason for models is to help make vendor interoperability. We all make layer 3 devices, they'll talk with each other. Make layer 4 devices, we know what they are. The other reason is to simplify learning, supposedly, even though the OSI model can make students fairly confused. The last but not least, it is to allow you to easily build new pieces. The OSI model, you'll find out the 7 layers, they receive services from the layer below them. They provide services to the layer above them, but they only talk to their peer layer on the opposite side. So when I go in here and I actually look at the OSI model, application, presentation, session, transport, network, data link, and physical models, when I look at these, from the sending to the receiving side, the layers only talk to their peer layer on the opposite side. In other words, I can be doing error checking at the transport layer and error checking at the data link layer, but those two layers don't know what the other layers are doing. The beauty of this is, if I need to rewrite the data link layer, I can just pull it out and stick a new layer in. That way, when I need to create a new Ethernet standard, long as it handles the ability to talk to the network layer above it and receive services from the physical layer below it, I can just plug in a new piece. So it allows us to have easy interoperability, okay, and a scalable design so that we can easily put pieces in and out. It's flexible, it's hierarchical. Same thing with network layer. Now that IPv6 is in, we just yank out the network layer for IPv4, shove in the network layer for IPv6, boom, we're golden. Everything's great. Okay? So, that's why we build models for our networking processes. Now, there are 2 models here shown on this page. One is the OSI model, which, by the way, if you need to remember, all people seem to need data processing. Alright? Or, that's layer 7 to layer 1. Or if you want to go layer 1 to layer 7, please do not throw sausage pizza away. Those are 2 ways to remember it with mnemonics. The TCP/IP model is Application Transport Internet Network, or ATN or A10. It's another way to remember it. We're going to show how these 2 actually relate to one another. But the TCP/IP model is not an exact duplicate of the OSI model because 2 reasons. 1, it was created before the OSI model. 2, it more closely actually shows the process of communication between 2 hosts. Okay, using TCP/IP, obviously. So here we go. TCP/IP model created in the 1970s. The application layer, and one thing you're going to learn, the application layer in TCP/IP model performs the functions of the application, presentation, and session layers in the OSI model. All right. The transport layer performs the same function as the transport layer of the OSI model. The internet layer performs the same function as the network layer of the OSI model. And the network access layer performs the same functions as the data link and physical layers of the OSI model. So, here we have it. Okay, this is just encapsulation using the OSI or the TCP/IP model. It's sent across a meteor medium, received on the opposite side. Now, this does not show the process of building the headers. Okay, this is what's actually going on. You have your email data. It could be a request, it could be an email. It comes in as a piece of data from the application layer. Okay, so here's the application layer data. It's broken, segmented into pieces. We put a transport header on it. Here's the data. It's called a segment. We move down to the network layer. All of the information from the transport layer becomes just payload for the network layer. Put a network header on it. Source destination IP address, source protocol, those types of things. That will then be sent down. That's a packet. Will be sent down to layer 2. There'll be a frame header placed on this. If it's Ethernet, it'll be a frame header that has the destination MAC address and source MAC address and some other things in it. And a frame trailer, which again, if it's Ethernet, it's a CRC or cyclical redundancy check, so that we can do error checking at layer 2. And all the information from the upper layers becomes data. And then finally, we send it out as bits at the physical layer, which is the blue-collar worker of the networking world. So, you do need to know the names of the protocol data units at each layer of this model. Data is just a general application layer for anything at the application layer. Segments are transport layer. Packet is the internetwork layer. Frame is the network access layer. And bits are the name for the information at the layer 1 of the TCP/IP model. Way to remember it is big freaking deal Sam. I say deal because deal is datagram. You'll see packet a lot of times called segment. Packets called datagrams instead of segments. Okay, so you can do it BFPS. That way you can remember it, and that would be bits, frames, packets, and segments, or datagrams. A lot of times you'll see it as datagrams. Here's a great example of how some of the interactive elements in the curriculum can help your students. There was a request for a web page. It comes in, it's data. We add the transport layer header. Okay, it's called a segment. We add an IP header. It's now called a packet or datagram. We add the frame header and the CRC. Now it's a frame. We send it out across the line, and we have bits. So this is the process of encapsulating information and sending it from the sending to the receiving. Okay. The only thing I wish I had done different here is reverse these two so that it was sending from the client to the server. This would be a response from the web server to the client. And here it is, sending it back to the web client, and you're going to watch the web client bring in the bits, check the Ethernet header, make sure it matches its MAC address, check the frame check sequence, make sure it has been damaged in transit. If it has not, it passes it up to layer 3. Okay. At this layer, at the internet layer or network layer, it looks and says, is this my IP address? If the answer is yes, it then looks and says, well, what upper layer protocol am I supposed to pass this up to? It will then pass it up to TCP, whatever happens to be, using the port number. And then from there, TCP will pass it up to the correct application layer process. And in this case, it's the web browser of the user, and they get the web page that they have requested from Cisco.com. So, here are 7 layers. Application layer provides end-to-end connectivity, and it is really the connectivity between the human network and the protocol stack. Also, one thing you'll notice is from layer 7 to layer 1, we're going from pure software down to hardware. Okay. Presentation layers, really shared representation. If encryption or compression occur, they occur at the presentation layer. Session layer allows you to create dialogues between two hosts, establish, maintain sessions. Transport layer, here's how I describe transport layer. Transport layer allows you to do guaranteed reliable delivery between two hosts, segmentation, error checking at layer 4. The network layer is just pure path determination. How do I get there? Data link layer deals with framing, okay, so how you exchange data using the framing methods at layer 2. And the physical layer is the bit pusher, so it just turns into ones and zeros. And here's how they relate. Again, the application presentation session layers map to the application layer of the TCP/IP model. Transport layer maps to transport, network maps to internet, and data link and physical map to the network access. Know this because it's on the chapter test, no doubt at all. Okay, so another packet tracer activity you can do. Here we're talking about addressing. What type of addresses do we have on the network? For the physical layer, like I said before, timing and synchronization bits. At the data link layer, we have source and destination physical addresses, which in an Ethernet world are frames. Framing is MAC addresses. Network is destination and source logical addressing, which most of what we do now is all IP addressing. We used to have to worry about everything from IPX, SPX to others, but now it's just basically IP addressing. Transport layer is source ports and source protocol, destination port, destination protocol. And the upper layers are just whatever encoded application data that you need to make sure the request gets to the correct application that it's working or asking for a piece of data. Alright. That's really the main item that we want to look at here in this chapter. The other thing is really what's called a port. And really with a port, that is the destination protocol and the destination port number that is used to make sure that on this server, because the server is running both FTP, it's running a terminal session, so RDP, it's also running electronic mail. When a request comes in, it's going to have a source and destination MAC address. Well, the MAC address is going to be the same. Okay, so the MAC address is the MAC address of the destination machine. The IP address of this server is going to be the same. So what it has to use the layer 4 port information to be able to know what application layer protocol to pass this up to. So terminal session data and port number, that tells it where to go to, and then it knows where to come back, because each request from the client will be mapped with a source port and a source IP address, source protocol, and all those items. This Warriors of the Net, that's a good little item you can show your students. You got to pull it up. You can just go and actually play the movie. So play that for your students. You can take a look at that. And that is chapter 2. Okay, communicating over the network. I hope you've enjoyed this lecture, and I hope you find it useful. Chapter 3 and 4 will be coming up shortly.